Hello, class. Welcome to week 3. So to summarize where we are in the course, we've talked about derivatives, and so between 140 and what we've done so far this semester, we're nearly done talking about derivatives. We'll talk about them a little bit again at the end just to review before the final. But for this week, we're going to switch and we're going to talk about integration, which is going to be a completely different operation on functions. So this week, there's really going to be sort of two disconnected pieces. We're going to talk about two flavors of integration. We're going to talk about indefinite integrals first, and I'm going to explain what those are. And then we're going to talk about definite integrals. And it's going to seem, for purposes of this week, like these two things have absolutely nothing to do with each other. And that is correct if you view it that way. But then next week, we'll get into talking about what the relationship is between these two ideas. So for this week, week 3, you should expect that you're going to see a series of lectures on indefinite integrals and a series of lectures on definite integrals, and then this will pique your curiosity in time for us to talk about why on earth someone would call both of these things integrals next week sometime. Okay. For the time being, though, let's settle in and talk about indefinite integrals. And so the first word I'm going to define here as part of talking about indefinite integrals is I'm going to define the word antiderivative. And so what is an antiderivative? So an antiderivative of a function f of x is a function, and usually I'm going to denote it by a capital F. And it's a property, or it's a function f of x with the property that if you take the derivative of capital F, you get lowercase f. Okay. So an antiderivative, as the name would suggest, is a derivative backwards. So what's going on here? If I'm given a function now, then I'm asked, hey, what's a function which has that as a derivative? Okay, so I want to do some examples of this. So let's start with what might be our favorite function. So let's start with f of x equals x squared. Okay. Now, aside, of course, we know that f prime of x is 2x, but this is not what we're interested in this week. We're interested in the antiderivative. So instead of saying the derivative of x squared is 2x, what we want to say is the derivative of blank is x squared. So that's really what this is asking. This is really asking us to find an answer to the question, the derivative of something is x squared. And we just have to figure out what that something is. And given that we've been talking about this for 4 minutes now, we don't have any really intelligent ways to do this yet. So I'm going to try and figure this out by guessing for now. So if I were to think about, well, what kind of thing would I have to take the derivative of for it to have an x squared in it? Well, I'd have to take the derivative of something like x cubed, right? Because remember, the power rule tells us that when you take the derivative of a power, the power goes down by 1. Right? So when you took the derivative of x squared, we got 2x. The power went from 2 to 1. I actually want to go the other way. I want to start with something with a power of 3 to get something with a power of 2. So I might try, hey, what if I just tried x cubed? Well, if I take the derivative of x cubed, That's actually 3x squared. And well, 3x squared is not x squared, so that's not going to work. But it does give me enough of an idea as to what I'm doing wrong here. Namely, I need to somehow deal with this 3. And the way I can deal with a 3 is by putting a 1/3 out front to start. Okay, and so if I take the derivative of 1/3 of x cubed, then I'll get 1/3 times 3x squared, which is just x squared. Okay, and so what's my conclusion? So big F of x equals 1/3 x cubed. This is an antiderivative of f of x equals x squared. Okay, so we've got one of them. But you'll notice I keep using this word an antiderivative rather than the antiderivative. And the reason for that is there's actually lots of other antiderivatives of f of x equals x squared. So let me give you a few more. So if I take the function g of x equals 1/3 of x cubed plus 7, if you were to take the derivative of this, you would get x squared as well. So this is also an antiderivative of x squared. And of course, I could also take something like h of x equals 1/3 of x cubed minus 2 pi. This will also, if I take the derivative of it, give me x squared. So all of these are antiderivatives. Now, this is, as it happens, going to get a little bit irksome if we were to just ask about antiderivatives, because it might be that I give you an antiderivative and you give me an antiderivative, and we give completely different answers. Like I might give g, you might give h, and it's not clear that these things are the same. And so we're going to sort of make all of this a little bit more concise by talking about what we're going to call the most general antiderivative. And so the most general antiderivative of f of x equals x squared is, and so it's going to be x cubed over 3, but then I'm going to write a plus big C here. And I'm going to write here where this big C, this is an arbitrary constant. Okay. And what you'll notice if you go back and look at the things we wrote down, and you probably noticed this before, all of our antiderivatives that we wrote down, this one and this one and this one, they all were just the same function, 1/3 x cubed, but then plus some arbitrary constant. And the reason that works is because the derivative of a constant is identically 0. So when we take the derivative, the constant just disappears. And so when we're talking about antiderivatives, most of the time, we're going to just spare ourselves writing down some constant, and we'll just write down a plus c. Okay, and again, this is called the most general antiderivative, and this is also what is meant by the indefinite integral. Okay, so we also call this the indefinite integral of f of x. Okay, and the notation for this is a little weird. So we denote it by, okay, so this is our integral sign. So this is our notation for the indefinite integral of f of x, which is exactly the same thing again as the most general antiderivative. Okay, so just to summarize everything that we've done so far, if someone asks you, hey, what's the integral of x squared dx? Well, the integral of x squared dx is x cubed over 3 plus c. Okay, so there are basically three pieces to the notation here that I need to make sure we're getting right. Okay, so first of all, at the front, we have this integral sign. And so this is telling me the thing I'm doing is an integral, it's an antiderivative. Okay, on the right-hand side, we have this dx, which tells me where the thing I'm integrating ends. So if you want, these two pieces together are like a parentheses, or a pair of parentheses. And it's also telling me what the variable is. So this is analogous to how when you wrote down the statement, the derivative of x squared is 2x, how this told you, hey, the variable we're talking about is x. Analogously, this piece tells us this in the integral. Okay. But also importantly, we want to remember that when we take an indefinite integral, we're always going to get this plus c here. And what the plus c is saying, remember, is that if you want to know which function has the derivative of x squared, well, that function is x cubed over 3, except that you could add any number to that. And so this plus c is to remind you, hey, you could add any number to this. It could be 7, it could be minus 2 pi, whatever number you like. Okay. So, I'm going to wrap up this video here for now, having talked about what an indefinite integral is and what the notation is. And in the next video, we're going to do a bunch of examples of calculating indefinite integrals of functions that we know. But until then, be well.